Doing recording. Here
we go. This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Hi, I'm Lee Bortons, and it's Monday, March 13th, 2023. Welcome to the Math Map Book Club, where Kirsty Gilpin and I discuss a math concept each week from our soon-to-be released math curriculum for families with students in classical conversations communities. So I was thinking about why I love math today, and I realized there was a time change had occurred, and I missed it because I was in a different time zone. And then I realized, well, I like time because it helps me figure out where I am and when I am. I also like it because before all this GPSing thing happened, I used to be able to look at the angle of the sun and tell what time of day it was and what direction I was going in. So I like math for that too. Kirsty, do you like math?
I do like math. So I thought I would share, true stories from my college days. When I talked about this, when we first talked about and compared our engineering experiences. And I always liked math just because it was straightforward, and I liked the notation. And I realized maybe that's because I'm lazy, but I like being able to communicate a lot of things with a lot less writing. And so although we talk a lot about how the fact that notation can be overwhelming, and it can be overwhelming for me too, it's also one of the things that I love about math is the clarity of communication with a simple amount of writing.
So that makes me wonder if before they stopped, used to be high school students studied shorthand. And that was a really difficult foreign notation. I wonder if that was helpful in their math studies. Oh, well, I like the notation because I don't know that you're lazy as much as you're a deep thinker, and it's too many words to write it down. So just a symbol is good enough. All right. Well, thank you for being here. So we only have, this is week 10, which means we have 5 more book clubs left before we take off for the summer. And I want to remind everybody to access the Math Map. You need to be a member of Classical Conversations CC Connected Community. Please feel free to participate in the discussion, even if you're not in CC. As Kirsty's good to put together these PowerPoints with Julie and share what we're going to be talking about each week. So we always have our exordium. And for those of you that aren't aware of it, you do have permission if you go to the CC Connected and get the beta to use the art that's there for the naturals. It's the same art for all grade levels, all domains. And you're welcome to use it as exordiums in your challenge seminars if you would like to start introducing the students to the Math Map. So tonight, what are we going to look at in the exordium, Kirsty?
Well, I left all 3 pieces there because it was hard to choose one. And so I thought that maybe tonight we could look at that and talk about the idea of intersection. And because clearly in the art, we see the intersection of 2 lines in the cross, but there's a lot of other things that are intersecting there. And they're hinted at by our quotation about the intersection of gifts and talents and abilities, discovering our purpose there, and as well as the crossroads, the cross, right, being where we meet Jesus. So I thought that might be if some people wanted to talk about when we think of the cross, when we think of our meeting Jesus there and the different intersections that may be going on all at the same time, if some people wanted to share some of the things that they saw tonight.
That'd be good. Yeah, I'll share one to kind of give them time to think. As a parent, we often say our children are passionate about things, and we forget that the root of passion, right, means suffering. And it's the passion of Christ. That's why it's called that. It's the suffering of Christ, and it's revealed in that intersection on the cross. And so it's interesting that it's that intersection of just intense delight and pleasure with the willingness to put up with the pain in order to pursue the things that God has had us love. So that's the intersection of pleasure and pain for our children as they're pursuing their passions. I bet Kirsty's daughter, Kate, I bet her feet hurt a lot of days when she's done dancing her ballet.
I was just thinking that, Lee, when you said that, the pain of point shoes, but the freedom of gliding across the stage. I am not passionate enough. I would never do it.
So if any of you think of stories or want to chat some in, we'll get to them.
I was just thinking about the intersection of cultures. There were the Jews and the Gentiles. And we've been talking about that as we're leading up to the Easter story, how, that really is what crossed the bridge from it being the Jews to being the Jews and the Gentiles. And so it was, in that it is the crossroads, it's the bridge over, that, but just that also just the intersection of culture. It was the Jews that hung him on the cross, but the Romans who physically hung him on the cross.
Sure. Yeah, I am always tickled by the fact that Jesus couldn't do what he needed to do for whatever reason. I'm not God and telling him what he can or can't do. But it wasn't until the Greeks on their own came to him and said, "Who are you?" That when after they left, he looked at his disciples and said, "It's time, guys." That's good. Good balance. All right.
I think there's intersection there, heaven and earth or life and death. I've listened to this morning's the Advent and our guest on our milestones and markers just kind of alluded to this idea that we don't sit in his death long enough to, we always rush to the resurrection and the life, but he died. He truly, he died. And so there was that kind of crossover there.
Jill, you want to share what your comment was?
Jill. Oh, yes. Go ahead, Jill. Share.
Just that being a parent is something that we are often passionate about. And there's a lot of joy, and there's a lot of reward, and there's lots to celebrate. And that just is those wonderful moments. But sometimes things are hard. It could be childbirth, or it could be the work of raising your children, or it could be everything you go through to adopt, or whatever it is, part of being a parent, however our particular situation is. There's the things that we weep over with joy, and there's the things that we weep over because they're hard.
That's true. And a lot of us are entering in like this crossroad between, or we're leaving a crossroad that I don't know that you're leaving till it's almost too late. And it's this, you go from being a child to a parent, and until you're done having children in your home, you don't realize what an intersection that parenting was compared to now that they're gone and you're not dealing with little children every day. And it's another new life that God breathes into you. So look at us. We have lots of intersections. Who knew all these life experiences were so mathematical?
That's right.
Right. So, and that relates to our two reasons that we think math is difficult is because it's a universal language, but too many people think it's only about calculations. And here we are trying to inspire people to think of just mathematically all the time. It's in front of you. It's in your life experiences. And so when we say math's beautiful, when we have those kind of life stories we just told, we can say, yeah, math really is beautiful. It's orderly, and we don't know the order all the time. So I just really appreciate Kirsty putting these discussions together to show you some of the tips and tricks that are in the order of the dimensions and the domains that we can go deeper into. Okay, so tonight we're talking about lesson 10, intersected lines. So Kirsty, what do you have for us?
So the first thing that I thought we would talk about, if you want to go forward a couple of slides.
It's thinking.
It's talking about it's thinking, yeah.
And then it went forward too far.
This is good. So here we are. Let's see if it'll go forward one more.
Now she's afraid to push it.
There we go. So a lot of times when we think about the grammar of mathematics, and we talk about what do you need to memorize, the thing that probably comes to your mind first are your math facts. And when we talk about math facts, we're usually talking about addition facts and multiplication facts. And tonight I wanted to talk about the fact that there's a lot more grammar to math that we can work on memorizing. And so here's a piece from one of the charts for week 10 that has all of this information about angles. And so take a look, and you really only need to look at the headings of this table. And what are some things that we could memorize about an angle?
Don't be shy, just shout it out.
The boundaries for what separates things from being acute, right, obtuse, straight, and reflex. Those boundaries, I think, are important because it's what defines you.
Okay, so right, so their classification. So there's really, let's unpack that and say there's two things there. Because one, I can memorize those definitions, right? I can say that a reflex angle is between 180 degrees and 360 degrees, or between pi and 2 pi radians. And I can memorize that definition. But I can also look at an individual angle, say 270 degrees, and memorize that it is indeed a reflex angle, right?
You mean looking at the image itself that is bigger, the arc is bigger.
Right. And so I could just memorize, hey, that's a reflex angle,
Mhm.
right? So what else?
Mhm. I also want to point out that's why just all the naming that we do with our children is so important, that we just can, every child that we have looks at things and names it. So math's no different. It just happens to be on a piece of paper.
So again, keep looking at those headings of this table. So we talked about at the angle classification. What else could we memorize?
We could see that there's different ways of describing those angles using like degrees or radians or revolutions.
So we could
I
memorize,
know that
yeah, we could
I
memorize.
was just gonna, sorry.
No, go ahead, Janice. Sorry, I'm talking.
No,
for
it's
you.
fine. I was just gonna say that that would have been really helpful for me when I was trying to dig into physics and I was using a scientific calculator and I was not getting the right answers when I was doing, and it was because my calculator was set to give me an answer in radians instead of degrees, and I didn't even know there were two different ways to name that. So,
And just FYI, in the math map, we have specific examples where the children have to practice that in their calculators.
So, so good. So you just pointed out, right? We've got angle classification. We've got degrees, counterclockwise and clockwise. You may not have picked up on what those little letters were meaning, right? And that's when we're in the actually in the plane, in the coordinate plane, we can either go clockwise or we can go counterclockwise. We could measure it in radians, again, same, right? Or revolutions, same, one way or the other. So there's one more heading up here that nobody has mentioned yet that we could memorize about an angle.
The image.
The image.
The image, right? So Julie, if you want to click through, you can, without clicking through to the next, you can list those.
What do you
So,
say? Oh, okay.
right, so the angle classification, the image, the degrees, the radians, the revolutions, we can memorize all of these things about an angle. And how is that going to help us to understand things? And what have I not talked about memorizing?
1,000 different things. Give us a bigger clue.
So Jana, what were you said something, right? You said degrees and radians, but what's not on this chart about degrees and radians?
Conversions.
Conversions, right?
Conversion.
So on this chart, we're not asking anybody to convert between degrees and radians. We're just saying memorize it, right?
Right.
Because if I memorize about angles, right? And I just memorized that a 0 degree angle is a 0 radian angle, right? I'm learning something without necessarily recognizing it, right? And I'm becoming familiar with that 0 degree angle. And then if I think about a 30 degree angle and I say, well, I know it's acute and I know it's pi over 6 radians and I don't know what that means, right? But over time, if I memorize this, I'm going to get to know these angles really well, right? And then am I going to get to know how degrees and radians work really well?
Yes, you'll have a good comparison of the two in your brain. It just kind of becomes intuitive almost. Like I remember when I was trying to learn Celsius degrees, I was an ER nurse and I knew that 98.6 was body temperature. And I had no idea how to convert to Celsius. I mean, I couldn't remember, is it 5 over 9 or 9 over 5? And do you subtract the 30? But I became familiar with, 37, that 37 degrees Celsius is the same as 98.6. And it gave me an idea of what was a reasonable answer. Like with this, if I'm trying to convert and it doesn't feel reasonable because I have this intuitive comparison of the two from having memorized some foundational things, then just makes it more doable.
I love that you use temperature there, because I had that same thing about Celsius. I was like, well, I know the conversion formula, but I didn't have that intuitive sense that you were just talking about. And still, until I started watching the weather on the BBC World Service, and they always did the weather in Celsius instead of Fahrenheit. And all of a sudden I went, oh, okay, now I'm picking up a sense of what they're talking about, right? And so I wanted to use that as an example that sometimes when we think about math, we are really quick and eager to say, what's the conversion factor? Let me do 100 problems where I'm converting from one thing to another. And that's not inherently bad. There's nothing necessarily wrong with that. But I wanted to point out that sometimes, right, the memory work that we look at without calculating, but just memorizing things, can be as powerful or even more powerful, right, to giving us that understanding about angles, right? If I start drawing, right, if I was to draw all of those reflex angles, and every time I'm drawing it and writing reflex next to it, even if I don't tell you what the definition of a reflex angle is, just by drawing those each time, I'm suddenly going to start going, oh, every single time I'm going more, right? I'm doing this bigger piece of the circle, right? So when we talk about grammar and math, it is very important. The addition and multiplication facts are very important, but I think you're going to see through the math map and through the flashcard sets that we're putting together that there's so much more memory work that we can give our students. And we really want to emphasize to them that this is not just, especially for our older students, right? Memorization feels like drudgery sometimes. It doesn't feel like fun anymore because you're like, well, just go memorize it, right? When we're with our little kids, we're like making it fun and we're playing games and we're shooting hoops and we're, right? And then we think somehow, well, they're in challenge 2, they don't need all those fun games that the foundations tutors are playing anymore.
They do.
But they do, right? That memory work is just as important, not just to helping us calculate, but just giving us that fundamental understanding of the shapes and the ideas that we're talking about. Because if our students if our students can look at that 30-degree angle and they look at it and they go, oh, well, that's about 30 degrees or pi over 6, right? And I'm not even trying to go between the two. I just have an intuitive sense that that angle is going to be about that, right? Then that's setting them up for success. And just what you said, Jana, like, okay, I did a calculation, but I know that's not the right answer, right? I've been using this example with a couple of different groups, right? We've got Chat GPT out there, and so I've read some things about epic fails, and I said, well, summarize my dissertation for me. And it wrote a beautiful summary that had really very little to do with my dissertation other than pulling words out of the title, right? ChatGPT had no idea. But if any of you had gone and asked ChatGPT what my dissertation was about, you'd think it was about something completely different than what it was, right? Because it has no fundamental understanding or judgment, right? And so what we want to give our kids, what we want to develop for ourselves is this sense of numbers and this sense of place and location and shape, right? This fundamental sense of what makes sense, what's right, right? So when we see something, we go, well, that doesn't make any sense, right? I may not be able to explain to you why, or I may not be able to calculate the exact thing, but man, something's off. Right.
Yeah.
So we want to build up that sense of discernment, right? The Holy Spirit gives us discernment about things that we can't see, right? In the it's a gift, right? But we can build up discernment for the things that we can see. And a lot of that's going to happen through memory work. So I just want to encourage all of us to look when we see tables like this, it's really easy to go, oh yeah, that table's there. But if we spend the time and we invest the time in memorizing it, the more that we do, the more familiar we're going to become, and we're going to be less reliant on always calculating in our heads to figure out where things go.
Something I would like to add is that this chart is here for a variety of reasons, but one is that one of the concerns I have about the curriculum is that students will start to say, Mom, this was the same problem as last year, or Mom, we keep using these numbers over and over again, the same ones. Well, that's totally intentional. We want them to know these numbers so well they get bored with them. Okay, so just a heads up.
Yeah, can you imagine if all your kids graduate and they know all of this information about all of these angles, right? Because if I know something about 135 degrees and 150 degrees, well, if I'm presented with 140 degrees, I've got some pretty tight boundaries for where that fits.
All right, let's move on. What's next?
I think it's our ad.
Oh, it's my turn. I'm not even ready. Okay, so I think I have this memorized and down. Okay, I'd like to thank CC Connected, where the Math Map booklets are discussed by the club can be downloaded by Classical Conversations members. I need y'all to look ahead to the book club schedule on leebortons.com under the Math Map book club tile, especially if you're going to miss any weeks and you get out of sequence, you know where we are. Because next week we'll be working on week 11, and I think you're probably finding it helpful if you can at least take a glance at what we're going to do before we do it. And also, it's just a reminder to you that the whole point of giving that out on the CC Connected at no charge was to help us to encourage our friends who maybe aren't confident about math to go ahead and take a look at it, because pretty much all the vocabulary they're going to work on through kindergarten through 12th grade math in the traditional math book, as well as in the Math Map, is in that one booklet. So be sure to visit it. Okay. Your turn, Kirsty.
All right. So the next thing that I pulled up for us to talk about, so this is again from one of those charts that we have for week 10, but this is from the first page, so we talked about angles. The two big ideas for week 10 when we talk about intersected lines is that when we have two lines that intersect, it makes angles, but then also the way that lines intersect. And I thought this was a good opportunity to talk about the fact that we talk about different grids in the Math Map. I'm going to turn my annotating tools on here if I can figure it out.
Meanwhile, if you want to know more about our grids, go back to the Math Map itself, and the blue bar on the left shows the ones that we'll be using that are rectangular throughout the curriculum. And then the off grid and the polar, there's some other ones that Kirsty will tell you about. But the blue bar going down the Math Map is to remind us of the grids that we have as our options. And there's not a lot of them to choose from when we're working in K-12 math.
So when we talk about our grids, and as Lee just pointed out, there's not very many, and we're going to look at two possibilities tonight. The first one is that we might be working what we call off grid. And a lot of times if you hear people, they'll talk about plane geometry, right? And I'll just write that there. And notice that it is A-N-E and not A-I-N. It is talking about geometry that is in the plane. And it just means we're not worrying about any locations. We're just talking about here's your plane and you're doing geometry. And so that's why up in this big section at the top, there's no grid. And it gives us a lot of freedom to explore some ideas where if I suddenly talk about it with location, it makes it a little bit harder. So when we talk about, for example, the images that you see there on the left are all drawn without a grid, right? So I can talk about parallel lines, and parallel lines are just lines that never intersect, right? And so I can take and I can draw these two lines, and when I look at them, right, I can say, well, at any point right here, if this is one distance and this is another distance, those two distances have to be the same. They're going to be equally distant everywhere, and they're never going to intersect. Well, if I talk about those lines in our rectangular grid, right, I can still draw two lines, but notice as soon as I put them in my rectangular grid, they're in a fixed location, right? And so let's say this is 1, 2, 3, 4, right? They're maybe not evenly spaced. And if I notice with this line, maybe I look at it and I say, okay, well, it seems as though I go up 1 every time I go over 2, right? So my change in Y, is 1, and my change in X was 2. And so my slope is 1/2. Well, if whatever happens to this bottom line, the same thing has to happen to the top line if they're parallel. If they're never going to meet, I have to discover that this is going to be the same. So they're going to have the same slope. Now notice up here, right, when I talk about that in this case, I don't really talk about slope because there's no reference point. So I'm just talking about two lines that are parallel. As soon as I'm in my rectangular grid, I can assign a measure, I can assign a location. So I can actually write these two lines as 1/2 X plus 3 and Y equals 1/2 X plus 4. And I could actually, can anybody tell me how many lines I could draw parallel to these two?
Infinite number.
Infinite.
An infinite number, right? So give me an example of another one that might be parallel.
1/2 X plus 2 million.
1/2 X minus 0.87654321.
8675. I thought you were going to start singing that song.
Right. And so we could all keep coming up with them, right? And we see one of them is going to be somewhere right around here, and one of them is going to be way, way, way up here. But they would all be parallel and they would never intersect. Isn't that kind of an interesting idea? The idea that they never intersect. They're all going in the same direction. It almost makes me think of like some dystopian movie where, like everybody's in gray clothes and they're just marching along, right? They're not thinking or interacting with anything else. They're just all marching along, never intersecting, right? So there's a way I can talk about parallel, both off grid and on grid. How many parallel lines would there be off grid?
You would have to measure each individual one above or below.
Right, there'd be an infinite number, but there's not really an easy way to describe them, right? So as soon as I put something in that rectangular grid, I can give it an address, I can describe it, right? And then everybody that's on the call could go through and say, here we go. I can name one. It's a lot harder to do off grid, right? So let's go ahead.
Kirsty, can I stop you for a second? Because I'm going to assume that people don't know what the y equaled 1/2 x plus 3 was. Did you go over it a lot last week? Does everyone know what that is?
Slope intercept form. Is that what you mean?
We touched on it, but we didn't go in great depth.
Yeah, so just real quickly for those that don't get it, if you put a 0 where the x is, 1/2 times 0 is 0. So the equation becomes y equals 3 and y equals 4, which is where she drew her lines.
Right, so those are the points. When x equals 0, right, y equals 3 and 4. Right. And so this part here tells me my slope all the time. And then this part is always telling me where it crosses my y-axis, right? What point on the y-axis. All right, I'm going to clear all of these drawings so that we can talk about perpendicular lines.
You have a question real quick
Yes.
from Melba. Why is it more difficult off grid?
So it wasn't necessarily more difficult, but there was no, right? If I have these parallel lines, there's no way for you to easily name another parallel line. Right? You could all come over and draw another parallel line, right? But you can't tell me where another parallel line is. There's no way for you to name it. And when I say name it, I don't mean like name the line like we would if we had points, but to give me a location of the line, right? We don't, if we're not on a rectangular grid, if we're not in a coordinate grid of some kind, there's no way to name its location. So we can sit there and say there's an infinite number of parallel lines, but there's no way that I'm going to be able to name or describe where they're located, right? Without everybody annotating and drawing them. So does that help?
Yeah, answer the one about the curve. Somebody had
Yeah, I
another
didn't
one.
see that.
Oh yeah, do parallel lines have to be straight, or can you have a curve that is parallel to another curve?
So usually when we talk about parallel things, just ignore me and draw, because just trying to move my chat box so I can see what you guys are saying. Usually when we talk about parallel, we're usually talking about parallel lines. But certainly we could describe, right? There's a sense of parallelness to these two curves because they're never going to intersect. And so the sense is there, but usually when we're talking about geometry and we use that idea of parallel, we're usually talking about lines or planes, things that are straight.
Can I throw in Kirsty because I have the question? So I would suggest that this is where we would talk about locus when they're curved or not.
Yes, we could.
Which
Maybe
is
not
another
tonight.
lesson.
Yeah.
This is for my own sake. You made me think of the lessons later in the book that we have. So I'll look at that later with you.
Yeah, we would. Yeah. So I think a lot of times we use the idea of things being equally distant from something else versus parallel. Usually we're going to reserve that. And yes, we have decided to use the name rectangular grid. Some people call it the Cartesian coordinate plane. Just like the complex plane is sometimes called the Argand diagram. We've decided to go with rectangular grid in the curriculum, and complex plane, and then the polar coordinates when we're talking about angles and radius. But we're not going to get there tonight. I'm just going to look at these two ideas. That's true, Donna. That idea of not intersecting is definitely different when we're talking about lines to other curves. Okay, so let's Let me get my drawing back on here. And then the next thing that's there is the idea of things that are intersecting, right? So I'm just going to, we talked about things that are parallel, right? They never intersect. If they're lines, they never intersect. And then we can talk about the fact if they do intersect and they're not coincident, they're going to intersect in just one point, right? And so I can draw, I'm going to just draw a couple of examples here, right, of lines that intersect and they only intersect at one point. When I'm talking about off-grid, again, I can look at these and I don't necessarily have to worry about where they're located. And sometimes that's more appropriate if I'm depending on the relationships that I want to examine between my lines. So if I'm interested, for example, in the angles that are formed, right, I may be easier to work off grid. When I do look on the grid, right? So let's look at, say, x equals 3 and y equals 2. Let's look at these two lines. So one is a horizontal line, that's my y equals 2. One is a vertical line, that's x equals 3. And these two lines are going to be perpendicular. And so we define perpendicular. If you look on the chart there, it tells us that it is 90-degree angle. Or we use this little box, right? So I could come up here and I could say, this is a 90-degree angle. And whether it looks like it or not, right, I can tell you that it is. And so that's one of the things that I would say when we talk about things that are off grid, you really need to pay attention to how things are labeled, because a lot of times they may not always be drawn accurately. When we're talking about things being in the grid, now suddenly, because location matters, right, we can use our analytical geometry skills to determine if things indeed are perpendicular. So in this case, let's look at y equals 2. And if I looked at the slope and I said that's the change in y over the change in x, right? How much does my y value change as I move along this line?
Doesn't.
It doesn't. It's 0. So it doesn't really matter what I choose for x, my slope is going to be 0. So now let's look at my x equals 3 line, right? Delta y over delta x. And what is my change in my x coordinate at any 2 points? Pick any 2 points, and how much does my x coordinate change?
It doesn't.
It doesn't, right? And so I wanted to point this out because one of the things that we talk about a lot in the math map is that back in 0D, what did we say about division by 0? Does anybody remember?
There's no division in 0D at all.
Ah, very good. How about 1D?
Yeah, I remember Lee saying that, well, you can't divide by 0 in 1 dimension, but when you get to 2 dimensions, you have to be able to do that. That's how you get, that blew my mind.
Right. So in 1D, when we were just doing arithmetic, we would all go, oh, well, it's undefined, right? We can't do that. But now in 2D, I still can't arithmetically divide by 0, but
right.
when I see an expression where I am dividing by 0, it has a different meaning, right? It suddenly has a different meaning. And a lot of times what we do here is we write this is infinity, because we're not talking about an arithmetic result here, but we're saying that my slope, I have an infinite slope. So all of a sudden I'm going from doing arithmetic to interpreting it geometrically. Okay. Notice up here in my off grid, right? Do I have a sense of what slope is? No. Right. That's something that's reserved for when we're talking about things in the rectangular grid. I can excuse me, suddenly put numbers together with this.
But Kirsty, could we off grid say that y and x, when you draw the box, that we at least know their slopes multiplied equal -1? Could you
Well,
still say that?
you could, but I would say it doesn't necessarily have a lot of meaning because we don't have, without the coordinate axes to give us a reference, you really can't describe slope.
But it doesn't go away because you do have that relationship of y and x. So I feel like I could say it equals -1, but I can't tell you why it equals -1. I can't prove, I can't demonstrate it.
Couldn't demonstrate it.
Mhm.
Yeah, that would be an interesting conversation to pursue because I
Yeah,
don't
later.
think you could define slope
Mhm,
and without a grid.
mhm.
Can you explain that? What are you saying? The slope of x and what, that equals
Sure.
-1?
Okay, so here, let's look at another example down in our rectangular grid. And let's look at, I'm going to try and make this a little, well, this one will work. This is y equals x. This is y equals -x. So my slope, here's one of our things that we talk about a lot in the math map are hidden ones and 0. This is really y equals 1x. And I've moved it over here. So it's plus something. So let's say plus 10. And this is really y equals -x. And let's say it's going to be -3. I really don't know because I just arbitrarily drew these. -1x. So if this coefficient is my slope here equals 1, and my slope here equals -1, which is the same thing as saying 1/1 and -1/1. And so one of the things that we discover about slopes of perpendicular lines is that they are negative reciprocals of one another. And so if I multiply them together, 1 times -1, right, and I'll write these as fractions, I end up with -1. So let's look at one where we, I know, Jana, that one is a little bit harder to stomach, isn't it? Yes. So we're going to say that that's not a case that we would necessarily always look at. That's one where you really want to see I have any number over 0 and 0 over any number, and they're reciprocals of one another, and the 0 is going to mush our negative sign, but we can still see that reciprocal relationship. So now let's look.
Jana, I do think 0 times infinity equals -1 to God. We just can't figure it out on our human minds.
Oh, that's good.
Oh, that's great.
So here we go. Here's a case that will work out more nicely, right? So again, I could write this as 2/1 and -1/2. Those are my slopes. And notice that they are reciprocals of one another. 2/1 and 1/2, and then one of them's negative. And if I multiply 2/1 times -1/2, I end up with -1. So that's a way that I can test in the rectangular grid if two lines are indeed perpendicular. Okay. So I got rid of all that. So I hope I didn't do it too quickly. But so we've talked about parallel lines, and we can talk about them off grid and we can talk about them on grid. On grid gives us the possibility of talking about where they are, their location. And we talked about perpendicular lines. And we talked about the fact that when we talk about them on the grid, we can use their slopes to test whether or not they're perpendicular. We've talked about oblique lines. And I drew them there, and I haven't really done a lot of work with them in the rectangular grid. But in the lessons, what you would discover is if I had two oblique lines, right? And again, I know their location, I can actually solve for the point where they intersect. I can find that one unique point algebraically, right? So again, once I have location involved, I can find this more specific information. Now, here's a case where maybe I find some things are going to be easier to do off grid, because I might want to look at this and I might want to tell you that this is 168 degrees. Let me make that a little bit clearer. 168 degrees. And I look at that and I go, oh, well, I know because the whole thing makes a line, it's 180 degrees. I can figure out that this is going to be 12 degrees. That is a lot harder to do in my rectangular grid, because now I have to figure out exactly what points, right? I can't make it up, because once I say these are the equations of my lines, I can't change the angle between them because that changes the equation of the line. So problems like this are a lot simpler to work with off grid, because I don't need to know where they are. I'm just looking at the relationship between the lines. If I start talking about them in the rectangular grid, there's a lot more pieces that I have to make work together. Okay. And so the last set, I'm just going to erase down here. The last set of lines that we're going to talk about are what we call coincident lines. And they're really just lines that line up on top of one another. We would maybe not see that as much off grid, but it's an interesting result that sometimes can happen when we're talking about the rectangular grid, because I might say, oh, well, I know that the equation of this line is, let's say 1/2 x plus 0. Well, then I might give you the equation of a line that looks like this. Oops, I didn't mean to write a y. Right. And now I could look at that and you might go, that's like a really interesting line that's in a totally different place. Right. But if I was to simplify this, I would find out that I get 1/2 x. 1/2 times 100 is negative 50. I add 50 to both sides, and I find out that it's the same line. So when I'm in the grid, suddenly it's a little bit more interesting to talk about coincident lines, because I can give them all different equations and find out that they're actually describing the same line. So when we talk about lines, I can have lines that don't intersect at all. I can have lines that intersect at exactly 1 point. So we've got 0 points, we have 1 point, and then we can have our coincident lines that intersect at infinite points. But guess what? In our Euclidean geometry that we're looking at, 2 lines will never intersect twice. So that's just a glimmer of some of the things we do in the math map, where sometimes it makes sense to work off grid, sometimes it makes sense to work on a grid, and sometimes we're gonna compare the two things.
And we even compare them to polar and complex also.
Yes.
One thing that, like, if anybody has any ideas from looking at the natural or the complex, it is really difficult to show the little kids what a coincident line is, because if you draw something on top of something, they can't see it. So we've done it like 2 different ways, with one line being thicker than the other, and then another way where we've used 2 different colors. So if you happen to stumble across those and have a preference, or have even another way graphically to reveal it, that'd be something really great to share.
Could you do a hot dog in a bun?
Well, we do things like that to try to explain it, but you know what? Somebody named Kirsty Gilpin maybe get rid of all of them because they weren't true.
So that is not a
No,
coincidence.
she didn't make me. We just hashed over, is there some other way we could teach the kids? Like we use really thin pizza with sauce on it, and it just never was quite right.
It's really hard to like how to talk about things that occupy the exact same space.
Yeah.
Right. Although, right. I mean, when you think about Jesus and intersections, right, he was fully man and fully divine. So in that same space, you had his physical body and you also had his divine nature.
Good
That-
ending.
That was
with
a good ending.
Yeah. Well, Julie, thanks for managing things. Thanks everyone for being here. We'll see you next week when we talk about week 11, which is curve lines, right, Kirsty?
Yes.
Okay, and we'll see you next week. Bye.
Thanks.